Humanity has officially built a spacecraft so fast that it will cross the terrifying void to another star system in less time than it takes a human to reach retirement age. Our current interstellar ambassadors are cosmic snails. Voyager 1 and 2 have been screaming through the dark for nearly half a century, yet they haven't even officially left our solar system's true outer boundary. At their current speed, it would take them 40 millennia to reach our nearest stellar neighbors. Chemical rockets are a technological dead end for deep space. But a radical fusion of directed energy physics and nanotechnology is changing the rules of interstellar transit. We are no longer talking about theoretical physics on a whiteboard. Engineering blueprints are finalized. We are building a fleet of ultra-lightweight, laser-driven microcraft designed to breach the interstellar barrier, hunt for alien life, and beam back the very first close-up photos of an exoplanet's surface. The race to the first real interstellar mission has begun. The blueprint for this historic journey relies on a concept called breakthrough starshot. Instead of building a massive, heavy starship, we are shrinking the entire spacecraft down to a single gram of matter. Meet the Starship. This tiny gram of silicon contains a power source, navigation systems, high-resolution cameras, and a laser transmitter. But it has absolutely no engine and no fuel. Instead, it hitches a ride on a sail. The propulsion engine stays right here on Earth. A colossal ground-based laser array will focus a 100-gigawatt beam onto the probe's sail for just a few minutes. The sheer radiation pressure of the photons slamming into the mirror-like sail will generate a staggering 60,000 gs of acceleration. Within minutes of launch, the probe accelerates to 20% the speed of light. That is over 100 million miles per hour. At this unimaginable velocity, the probe will cross the interstellar abyss to Alpha Centauri in just over 20 years. But surviving a 2-decade trek through the interstellar void at 1/5 the speed of light is an engineering nightmare. In the deep dark, empty space is far from empty. When you are traveling at 37,000 miles per second, colliding with a single grain of space dust carries the kinetic energy of a hand grenade explosion. The probe's leading edge must be armored with a layer of magnesium oxide to absorb these catastrophic subatomic impacts. Then there is the threat of radiation. Stripping through interstellar space exposes the microelectronics to a relentless bombardment of high-energy cosmic rays. The onboard AI must constantly patch its own corrupted memory files, steering the probe autonomously without any help from mission control back home. After 22 years of silent travel through the frozen dark, the probe finally reaches its target destination, Proxima Centauri b, a planet sitting dead center in its star's habitable zone. Because the probe has no fuel to slow down, it has only a few hours to gather data as it screams past the planet. Its multispectral cameras will analyze the light bouncing off the surface, scanning for the distinct chemical signatures of liquid water, oxygen, and potential artificial structures. But gathering the data is only half the battle. The probe must then use its light sail as an antenna to beam those historic images across 4 light-years of empty space back to Earth, using a laser that outputs less power than a standard smartphone flashlight. We have spent decades engineering the perfect scout, but the laws of special relativity have hidden a devastating, tragic twist that means our first interstellar photos might arrive back home completely unreadable. Or worse, we might already be obsolete before the probe even arrives. This is the weight calculation paradox. If propulsion technology advances exponentially over the next 20 years, a faster, heavier starship launched a decade after our microprobe will inevitably overtake it, arriving at Alpha Centauri first. Furthermore, at interstellar distances, the tiny laser signal spreads out across millions of miles of space. If our receiving arrays on Earth suffer even a microdegree of misalignment, or if the probe encounters an unexpected cloud of dark plasma, the signal drops below the cosmic noise floor. We could spend billions of dollars launching our first cosmic scout, only for it to vanish silently into the dark, sending back data that humanity will never be able to hear. The first step to another star is already being built. We just have to hope something is listening when we call. If you want to stay updated on the absolute bleeding edge of deep space exploration and starship engineering, hit that subscribe button and smash a like right now. See you out in the deep.